Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Center of the Federal University of Pernambuco in Brazil, and has a PhD degree in computing from the University of Glasgow, in Scotland, in the UK. His main research interests are in the area of programming languages and compilers, in particular functional programming and functional languages compilers, and the talk today is on integrating Haskell with .NET using Rotor.
Hello. By the group of Nigel Perry there, and but we have quite a few differences and actually similarities and differences from some of the results that were presented today and yesterday. So it's quite interesting to compare the works. Well, the motivation is similar to what was presented yesterday. We wanted to take advantage of having Haskell implemented for the .NET platform. I mean, to make it be able to interact with other languages more easily. We wanted to have better integration with .NET components and tools. I mean, we had done some work on integration with Visual Studio and also other kinds of components. It should also be interesting to see the performance results. I mean, there are implementations that are based on using bridges, and we wanted to compare a bit with that kind of work, and also that's not a native implementation for .NET. And also, I mean, you can probably find lots of previous implementations of Haskell or mentions of Haskell being implemented, even in Project 7 from when .NET was released. But actually, you don't see much documentation or much information about all these previous efforts. I mean, obviously there are some, but there is actually little or no documentation on that. I mean, there were previous work done by Nigel on the Mondrian, related to the Mondrian project. There was work by Don Syme also in Microsoft Research that did also some porting. But I mean, if you go after the details, there aren't that many details or information available on these implementations. Mostly also there are partial implementations. Some of these, I mean, they support a bit of the prelude of Haskell. Some programs can be compiled, but doesn't support let's say the Haskell standard. And also, I mentioned the limited availability. I mean, if you try to get access to these implementations, they're not available from the Haskell source or anywhere else where you could actually look, or if they're there, they're not being, I mean, easily compiled and easily being used, easy to be used and compiled from the Haskell source, from GHC, for example, from the Glasgow Haskell compiler. And I mean, obviously, there are many other implementations of functional languages for .NET. I mean, there is Scheme implementation. There is F# from Microsoft Research too, SML.NET, Mondrian, which has lots of functional characteristics, and other implementations. Nemerly has some functional components too. But I mean, Haskell also has some quite big differences from what you would do in an F# or a strict functional language implementation, because it's a lazy language. Then you have lots more of closures, lots more of usually partial applications in the source code, and then it's really something that's expensive to evaluate and quite different from the regular strict functional languages. Another strong point of trying to do it properly for the .NET platform is that, I mean, the .NET platform has some things that the implementation for JVM for Haskell that were also developed that don't have. I mean, like the focus on this interoperability between other languages. I mean, the JVM was originally focused on Java. The support for tail calls in CLR, which is actually, we had similar problems to what's mentioned in the previous presentation. I mean, we had the tail calls have a cost, actually, instead of improving the performance. They're really, I mean, you pay a cost for using tail calls. And also the support for function pointers. That is also something that CLR has, but that you don't have from the JVM. Well, there were quite a few design decisions that we did. We looked at the traditional ways of implementing functional languages. I mean, we have the push-enter model where you push the arguments in a stack and then you enter the closures for evaluation. And there is the traditional eval-apply model where you evaluate the closures and then apply to their arguments. Actually, there are recent results that showed for the native Glasgow Haskell compiler that the two implementations, they have similar costs. So we decided to go initially for the push-enter model, but we may have to evaluate maybe an eval-apply implementation later because of specific characteristics of the CLR. For data type representations, there are also, I mean, we could have chosen to represent, a list with as a class for list and a class for cons, a class for nil, and class for each of the constructors of a data type. But we started using a common container, so you have a class, or actually a few classes that work for classes with one component, two components, three components, like tuples and everything. So these are shared instead of having lots and lots of classes being created. And that was chosen because we were worried about the number of we didn't want to start creating too many classes, so we tried to share as much as possible the implementation. And for closure representation, that's another big issue that was also discussed before. Well, for closure representation, we have usually we can find these three options mainly. I mean, we have the choice of using one class per closure, where it's this next slide here, where, for example, you have closure 302. I mean, one class per each new closure in the program, and then you have, if it's an updatable closure, a closure that will have a value after it's evaluated, then you have this somewhere where we store the value of the closure, and then you have a method that will enter the closure, and then checks if the value is available, or if it's available, return it. Otherwise, it would evaluate, calculate the value of the closure, and update the value, the value variable there, the value there, and then return that value as a result. The problem with this is that you create hundreds and hundreds of closures easily when you're running, or you have many different closures in a Haskell program. So so we were afraid of creating that many closures and the cost of closure of this class loading mechanism, and then we tried to make use of a common single representation for closures. And that could be done either using, if you use a function pointer, but then we would have unverifiable code, which we didn't want. We're trying to go for verifiable code. And the other option actually is using delegates, which is this type-safe mechanism for having reference to a code. And also we had the information that there was a better performance for delegates in .NET 2.0 as opposed to the previous implementation. So based on this implementation, the idea would be, instead of having the code, this enter code for each different class, you would have a delegate there, and when you create a new closure, you pass the delegate with the code for that closure, the code that evaluates that closure. We actually went one step further. Instead of having a delegate a variable that is a delegate and evaluates this result, we decided that we would actually inherit from the delegate class, and actually that would avoid having another pointer and another object, because each delegate creates another object in the heap. So we went for this implementation where we have the class closure that inherits from the class delegate, actually class multicast delegate, because you can't inherit from the delegate class. And this can't be done. Actually, this is pseudocode in C#, because this can't be done from C#. So we had to generate this using the EIL code. So we have this code there where, we have this enter method which checks if everything is okay, the number of arguments and everything, and supports the partial applications of functions and everything, the partial applications of arguments and so on. And if everything is okay, then it calls the value of the delegate, which really does the calculation and updates the closure, if it's a thunk, an updatable closure. So that was the solution we decided to evaluate. We went for it, So we have these updatable closures where we have a value field that is the value after the closure after updating. For non-updatable closure, we keep fields for arity information and for partial applications when we have partial applications of functions. And we keep in these closures the set of free variables if they have that they need to access to be evaluated. And the delegate code, I mean the code that's really invoked, that is passed when we create this closure, it points to what's called this low entry point, which does all this checking of whether all the arguments are in the stack, whether if it's a partial application, and various other checking that has to be done before you evaluate the closure. So when we already know which closure we'll be calling, I mean if you have the access to the information about which code will be called, then we go through what's called a fast entry point, where we do the jump directly to the function that is being to the code of the closure, that we don't need to go through the delegate. But anyway, I mean this is sort of the structure that we have. I mean we have these a set of updatable and unupdatable classes for representing the closures, and they have these values, and they have the variations are basically on the number of free variables that are available. 1 free variable, 2 free variables, instead of just to avoid having an array of free variables to improve the representation. And then we have these common spec structures there that are used for representing the data structures after evaluating. I mean, if you have something that's was not initially defined as a closure and evaluated later. Now, just to give you a few of the kind of code that is actually generated, I mean, this is the code for map. I mean, this is using the internal representation of the Glasgow Haskell compiler, which is called the STG machine. And then this code, I mean, it's a non-updatable closure for map, a non-updatable value there. It has 2 arguments, f and the list, and then checks if the list is an empty list, returns an empty list. If it's a const cell, then it creates 2 other closures, an fx closure with 2 free variables, f and x, and the other one, fxs, which has 2 free variables and calls map back and creates a const cell. Well, this code is translated again in pseudocode because we're actually generating IL code because we wanted to make tail calls, and tail calls are not available explicitly from C# code, and again, that was another decision to use the IL code. And then, I mean, this is source code. You have these 2 parts. I mean, you have this non-update, this slow entry point, which the code is not there. That checks if all arguments are passed in the stack, and if it's a partial application or not, and all the information when you really don't know which function information about the context where you're calling the map function. And there is the other code, which the second bit, that's also a call to the map function. And then it has, I already know that has 2 arguments. Then it passes explicitly the 2 arguments, the f, the function, and the list, which are both closures. And then it has all the evaluation of entering the list, entering for to evaluate the closure for the list, and then evaluates if it's a nil tag or a const tag, and then creates all selects the components, the x component and the xs component, and then creates the other necessary closures for the evaluation. So this is the kind of code that's being generated in the approach that we did. For the implementation, I already mentioned that we actually decided to use an existing compiler, optimizing compiler for Haskell, I mean the Glasgow Haskell compiler, which already has all the optimization, lots of high-level optimizations and transformations in the code, and all the front end of the compiler is available. And it generates in the end the STG code, which is the intermediate representation language. For Nigel's work, he used the core language, which is a bit higher level than the STG. The STG already has explicitly all the closures that are going to be created, so we already had, at this level, we have all the information of all the closures that would be created. And since we're using a model that's really based on this traditional compilation of push-enter model and all the details of the traditional implementation of a functional language, STG was had more information that we could use to going forward in this implementation. So that was our decision to go for STG. And for generating IL code, we needed these tail calls. We wanted to use tail calls. We had this decision. And also, I mean, these extensions also let us somehow, although this is not generated by the compiler, but we had to write some IL code for extending the delegate class and other things that we really couldn't be done through C# and couldn't be done through C# directly. So what is the current status of the project? We have support for parts of the Haskell prelude working. I mean, we can compile quite a few of the base of the prelude. I mean, in the Glasgow Haskell compiler, this is split in quite a few files, and most of these files are being already compiled by our compiler and generating .NET code, verifiable and everything. But we were really just starting to evaluate the effects of the performance. I mean, having just a few programs that were really going deeper and looking at the performance results. And the performance results, we are expecting for better results, but I'll show you some initial performance results that we have. Actually, this is just a set of 8 programs, and then I mean, most of them, there are 2 outliers there, which are, I mean, more than 10 times slower. But these, at least one of them, is actually just some top-level constants that are not being garbage collected due to a detail in our implementation. So if we do the proper, we have already made some tests, and if we do the properly the proper change in the compiler, that should go down to around 10 also. So we have something, I mean, for these 8 programs, we have something around, in the average, I'd say 5 times is lower than the native GHC implementation. We believe there is room for improvement there. I mean, we haven't really gone that deep in the evaluation of the programs, but we feel from what was presented just before this presentation, I mean, that we have some costs that are being there, like the tail call, the use of tail call, which is more expensive than the regular calling mechanism. That's a price that's being paid there. And also this use of delegates. I mean, it's too expensive to really use, still too expensive to use delegates for the implementation. And that could be something that could be improved by other approaches. I mean, just summarizing some of the things that I've mentioned. I mean, this CAF, this cost of the common applicative forms, the cost of these objects that are being kept there, that can be easily fixed. We are working on that right now. We have this large cost for delegates. I mean, large objects for delegates, and the highest cost on the execution that we could measure was exactly the creation of the delegates. So, I mean, and we believe that maybe if we extend the rotor or having some specific implementation for closures, that this could be reduced, and we could use some representation that has pointer to functions, I mean pointer to code, like a closure might need, but that could have a lower cost than using the delegates or inheriting from delegates directly, which is what we've done there. Things like updating in place, which is also not possible. I mean, in this implementation, use delegates, and the cost of tail calls, which I already mentioned. For tail calls, there is yet another issue that I mean, the CLR specification, it doesn't guarantee that tail calls will remove stack frames while they're being executed. I mean, it works like a hint to the execution engine. So it would be interesting to have that more detailed on the implementations. I mean, sometimes it's not documented what's really done for tail calls, where it's supported in all the contexts because it's not demanded. So that's something that should be more detailed. And also, I mean, there are some restrictions on fully trusted environments, which we found that somewhere in the documentation or in some discussion. And that can also be a problem, because if you don't remove the stack frames, then for a functional language where you have lots of recursion, that might end up having problems with stack overflow and problems with performance, of course. So tail calls is something that we have to investigate how it is supported in .NET 2.0, for example, in the implementation and in Rotor. I was talking with the group this lunch, and they mentioned that it's probably properly implemented for all the cases, but we have to check all the details. And another cost that we have is using this push-enter model. We need a separate stack for passing arguments, because you can have partial applications, you can have applications of functions with more arguments, I mean, in some case. So we need to keep track of another separate stack in our implementation. That also adds cost. If we move to an eval-apply approach, maybe we could avoid paying this cost of having an extra stack, and that's another hidden cost of this implementation. So there are many things that we intend to experiment and evaluate and see which kind of improvements we can manage. Other, practical difficulties that we had was the fact that we had to work with the beta version of .NET. We use generics in our implementation, and we had difficulties finding profiling tools for heap profiling, for execution profiling for .NET 2.0. Even it's really difficult to find free tools, and even some commercial tools. It was quite limited, the availability of what we could find. The Rotor for .NET 2.0, which is not available. We don't have a beta or anything. That would also help if we had some beta, just like we have for the real code. And also, we have to do some work on the interaction of C code that is embedded in the implementation of in parts of the prelude of the implementation of the Haskell prelude. But that can be done. We have taken that on a case-by-case basis. So for the next steps, we're going to work on fixing this problem that I mentioned with the performance of CAFs. Evaluate changes in this delegate inheritance mechanism that we're using. We're trying to see what kind of options we have and compare the performance gains of other alternatives to that. Investigate this tail call, if there are really these tail call limitations and the overhead of tail calls in .NET 2.0, which was mentioned in the Nummerly talk just before. Possibly see if we can extend Rotor with a proper support for closures. There are suggestions of that and discussions of that even with Don Syme's implementations for Haskell, which also discussed this thing of having a specific implementation for closure and support for closures inside the CLR, the implementation. And that would be something that would be interesting to investigate and to see how much can we get of performance out of that. And also the interoperability of Haskell to other languages, which wasn't really the initial objective, but that's something that's very important. Once you have a .NET implementation, how are you going to do proper integration of Haskell, calling .NET code, and vice versa, how you expose these things. And there are quite interesting works from other functional languages like F# and other SML.NET and other implementations. So that's something that you can learn, and we can see how we can do better use of that. So basically, that's what I had to present. Are there any questions?
All right. Well, first let's thank our speaker. We actually have a little